In the previous lesson, we talked about fluency for addition, subtraction within 5. And now in this lesson, we're going to talk about extending that work for numbers within 10. And some of that is going to sound familiar because some of the same kinds of things that we do with smaller numbers also applies as we work with larger numbers. To truly understand a number, for example, will require us to be able to do decompositions. So some aspects will be familiar, but I'll be attempting to highlight some of the new considerations that we need to make as we move into slightly higher numbers. As we go through today's lesson and also the very next lesson, they're the last 2 lessons of this PD module, and I've intentionally tried to help you see how everything ties together that we've been studying so far. This is a nod to the Common Core authors' intention for the standards to be extremely focused and also coherent. So in terms of focus, I'm trying to help you see how the kinds of things that you do all connect with one another. And also in terms of coherence, I've tried to foreshadow how these things will be used in the future so that you can see where it's going next and why certain things are so important at the kindergarten level. So for working within 10, we're just going to go back real quickly and look at the particular operations and algebraic thinking standards that specify within 10. And we see 2, 3, and 4 have some reference to being able to do this within 10. So in standard 2, we need to be able to add and subtract within 10. It doesn't specify with fluency like it does within 5, but they should certainly be getting experience, and it's reasonable to expect that some of students in your class probably will be getting to the point where they know some of those facts fluently, even though they're not required at this level. For example, many students get 3 plus 3 is 6 and 5 plus 5 is 10. Those are very fast, easily learned facts by many children. We also know that they need to decompose numbers, and the decompositions, they should understand numbers well, but if you can make it through all of 6 through 10 where they really understand how to break it apart into pairs, that would be wise. Now, if you look at standard 4, you see that 10 is one of the numbers that they have to learn the decompositions for. But 9 may be a number that you get to some years and not to others. It depends. It's more important that students understand numbers really, really well than that they get through all of the numbers 6 through 10. 10, on the other hand, knowing the number combinations that make up 10 is extremely critical. I've mentioned this before, but in first grade, they're expected to start learning how to use level 3 methods such as make 10, and it is impossible to use make 10 well or for children to feel comfortable developing that strategy if they do not have quite solid at that point their sums of 10. So there should be some efforts towards getting those sums of 10 solid. Some of that fluency work can continue to occur in the early first grade year, but if you leave it all for that time, it's unlikely that children will be able to get to the level 3 methods. So we make a good effort in kindergarten to do that. All right, so I mentioned that we were going to talk a little bit about how working with numbers 6 through 10 is a little different. In Part A module, where we talked about counting and cardinality, we also discussed subitizing. Subitizing is pretty common in the research literature, and the Common Core authors specifically describe learning how to subitize, and working from conceptual subitizing to arithmetic strategies is a critical progression in the kindergarten first grade sequence. So subitizing is specifically stated by Common Core authors, but a lot of teachers are not yet very familiar with it. And so it's this idea that you can just see certain numbers. Now, I don't have time to go into a great deal of detail, but I will tell you that many children can subitize. Certainly when they arrive at school, many can subitize 1, 2, or 3 items. That means when they are shown 3 items, they often recognize that it's 3 without having to go 1, 2, 3. They just look at it and see it's 3. Now, a number of children can also do that for 4 and 5, and a number of children who couldn't do that on day 1 of the school year learn how to do that, say by mid-year. Even adults find it extremely difficult to subitize beyond 5. Typically, if you see a group 6 through 10, in your mind's eye, you partition the group. And it can be done so quickly, you hardly even are aware that you're doing it. But if you look at a group of 6 items, you might have seen it as 3 and 3 or 4. And, well, I see 4 over here, and that's kind of 2 over there. And then your mind constructs the fact that goes with it. And it can be very fast. But you typically don't look at 10 pennies and say that's 10. Right? Even as adults, we can't really do that. This makes working with 6 through 10 fundamentally different for children than working through 1 through 5. It increases the challenge, but it also increases the opportunity that they're going to really attend to some mathematical relationships that they might have gotten by without really noticing or dealing with for the smaller numbers. However, we need a way for them to really develop meaning for these, because for a young child, 6 through 10 might as well be a much larger number. There's not necessarily an understanding of how 7 is much different than 9. And if you think about it from an older child's perspective, imagine a 4th grader probably doesn't understand a great deal of difference, really, when it comes down to conceptualizing between a million and a billion. They might know that a billion is more than a million, but by how much, that it could be a little bit, right? They don't really understand how these two quantities relate to one another. And that's the similar kind of idea for kindergartners as they work with 6 through 10. It all kinds of runs together. It's just bigger numbers, but very, very general. So some recommendations, and this is discussed in 2 different documents that I'm referencing here. This one uses finger patterns. So the recommendation for getting around this idea that the bigger numbers run together is to use the relationship between that number and 5. This is called, in some sources, the 5 groups, and in some sources it's called the 5 plus n pattern. But it's essentially recognizing all the numbers 6 through 10 in terms of their relationship to 5. So 6 would be 5 and 1 more. 7 would be 5 and 2 more. Okay, so recognizing that, and here you see actually 3 representations. The numeral, which really doesn't give us any insight about its reference to 5. You then see what amounts to a 10 frame, even though the frame is missing. The dots are arrayed in that fashion, so a dot array that's like a 10 frame, and then you see the finger pattern. And getting children to be able to relate the finger patterns that they're showing to this idea of how much is it in reference to 5, and then relating that to the numeral. The Common Core authors, that was from the Focus in Kindergarten Curriculum Focal Points. This is the Common Core, and they also discuss this particular pattern, and you see an array pattern here. This particular graphic comes directly from the progressions on page 10, and you'll see them discussing the exact same idea. Now, they also do mention that fingers are a good idea, but the Common Core authors have a little proviso there, which is that the finger patterns are so familiar that children may not have actually stopped to think about how the finger patterns reveal the relationship to 5. For example, if they show 9 on their fingers, one hand has 5 and one hand has 4 fingers. Can they think of that then as saying a 9 has a 5 and a 4 in it? That is really important. I'm going to tell you about a kindergartner. Now, mind you, this was a pretty bright little girl I was working with one day. And she was playing a game where she had to double the amount on a dice. And it wasn't very challenging working with the 6 dice, so I gave her the polyhedral dice. She rolled a 9, was unsure, looked at her hands, saw the 5 and 4, and said, oh, it's 18 because 5 doubled is 10 and 4 doubled is 8. So here you see how recognizing the 5 patterns can be very helpful in terms of arithmetic strategies. And that's exactly one of the other reasons that the progressions document, the Common Core authors specify that the 5 plus n pattern is useful. Not only does it help children develop a sense of feel for the quantity, but it also can support them in developing more advanced arithmetic strategies, including level 3. So I gave you one example of a level 3 strategy with the girl who doubled the 9. Here's a couple of visual representations. That child used her fingers. Here you see a couple of other visual representations that can reveal some interesting patterns in relationship to 5. And these are two different representations, but for the same idea, which is 6 plus 6. So on a math rack, also sometimes called a reckon rack, if you have 6 on the top row and 6 on the bottom, when you look at it, you see 2 5s and you see 2 1s. So you can think of that as a 5 and a 1, a 5 and a 1, or 10 and 2, and know that it's 12. And then I've also shown that with the tens frames. So these are two kinds of tools that have an inbuilt sense of tenness that can help children attend to what a number is in terms of 5 and leftovers. And that is a very valuable source of dialogue and attention in your work with them. There are some other big ideas. Now, the big ideas that are specified here are equally true for small numbers. It's just that because children can oftentimes subitize small numbers, they haven't always put it all together that, that these are true, because sometimes their own just intuitive understanding of number comes to the forefront instead of thinking these things through. So as they work with bigger numbers and these ideas crop up again with larger numbers, they begin to see that the adding one more is just the same as saying the next number in the number sequence, and that if you add 0, you don't move anywhere in the number sequence, you stay where you are. So those can become more apparent as well. Now, key components to working within 10 that still work with some of the same ideas that we've already talked about are multiple representations. Just as that was true for smaller numbers, it continues to be true here, especially using some numbers, some tools, as we mentioned, that can build this idea of fiveness. Varied practice. We still want to have some number talks, we still want games, reinforcement tasks, and we want to integrate these number sets into problem-solving experiences, especially with the 4 designated problem types that we discussed in the first lesson. We want to have a lot of dialogue about the representations, using a variety of tools. Making connections between representations is critical. Seeking patterns, discussing different strategies, how we came about to getting a solution, and looking at number relationships. So the dialogue continues to be important, and then not only making connections between representations, but perhaps concepts as well. Seeing how the commutative property, for example, plays out in one situation and then another as well. How it looks on this tool and that tool. So here I actually show a variety of representations, and in the center is the relationship that we're unpacking, and that's the number bond. We're unpacking in all these representations the idea that 9 can be decomposed into a 5 and a 4, that a 5 and a 4 together make up a 9, that if you have a total of 9 and you know that 5 of them are in one set, the remaining set is 4. So in the top image we have a math rack, and you can see easily the 5 and the 4. And here it is an expression. The Common Core authors have indicated that children need a lot of experience working with expressions and not just equations, so that they understand that an expression hangs together. It represents a chunk in an equation that is together. So this is a set of 5 and 4 joined. All right, so that's what I have here, is a set of 5 and 4 joined, and that so happens to be the same as 9, and that's why we can put an equal sign there. We also see this represented in a 10 frame. You see the 5 and the 4 there. I have it represented in a subtractive situation with 9 orange dots, 5 of which are crossed out. And then I also have it in what's called a tape diagram at the bottom in blue and purple, showing that 5 blue cubes and 4 purple cubes all together, or they look more like rectangles, altogether are 9 rectangles, and then the equation. So we have a whole variety of different representations there, some more concrete and some more abstract. Okay, now we're going to shift slightly into a different aspect of this lesson, but still talking about the idea of 10. But instead of thinking also about 6, 7, 8, and 9, right now we're going to shift entirely to knowing the combinations that sum to 10. And these have a variety of names, and I'm not sure what your text calls them, but some of the common ones are calling them sums of 10, friends of 10, combinations of 10, number partners that make 10. There's a whole variety of them, but they're pretty familiar to us. So now this is specified exactly in Standard 4 of the operations in algebraic thinking domain, and this idea that we can pull 10 apart and have many different hidden partners there ties in directly to our cluster, where we're talking about taking apart numbers and putting them back together. Right now, we know the sums of 10 are really critical, and we know that children need to have made some significant progress towards internalizing these sums of 10 by the end of kindergarten. So what we really need to look at are some strategies for how to do that. And as we've discussed in previous sessions, distributed practice is far more effective than just having a few lessons deal with this topic and then moving on. So think about some ways that you can do that. Number talks are one thing we've discussed already as being a place where some of your ongoing topics can be regularly cycled through the number talks, but there are other ways as well. So we're going to discuss some of those. The morning routine would be one. I've seen a lot of people who have like sticks or straws, and they collect 10 and then create a bundle. That's really useful when children get a little older. This idea of bundling and unbundling groups of 10 will become very important. In the meantime, however, it would also be very useful to represent the days of school with 10 frames. And the reason for that is that you're going to get an understanding that's less apparent with the bundles of 10. If I have 7, it's not immediately apparent to me that I need 3 more to make 10. However, if I'm using a 10 frame and I have 7, like in the bottom one that has dots in it here, you see there are 7 blue dots. Well, I can see easily that I'm going to need 3 more to complete that. So imagine a classroom where they use these sticks and they're doing the bundling, and they're also representing it by adding a sticker to the 10 frames on a days of school 10 frame chart. Then they can say, look at the chart, how many more are we going to need? And the children can then say, perhaps in a choral sentence frame, there are 7 loose straws. We need 3 more to make a bundle of 10. So there can be a couple of blanks there, and the kids can construct each day until it becomes quite familiar to them to think of, I have this many loose ones and this many, and pretty soon I can make a group of 10. This particular book is well suited to introducing this idea of sums of 10 with a lesson investigation. Even though lessons are not necessarily suited to intensive long-term learning, which children need, they can still serve a role. And then it can become a math center where children work with some concrete objects to represent the fireflies. In this particular book, there are 10 flashing fireflies, and on different pages, there are different amounts in the jar and outside of the jar. And so in the representation I've shown here, there are 6 inside the jar and 4 outside the jar, and 6 and 4 then is a combination that makes up 10. So as they work through the story, you can initially read it, and then they can act it out, and it can become a center where they explore all the different sums of 10 that they can figure out. Now, there are a variety of games that can be used as reinforcement tasks, and once children understand the game structure well, as far as repeated practice goes, they can go home and teach it to their parents or to siblings. 2 games that are very easy to do this with are Go Fish for sums of 10 and Concentration for sums of 10. Now, earlier in this and I think in the previous lesson we talked about using those for sums of 5, and you do that with the 5 frame cards, and when that's no longer challenged, then the game can kind of grow up into now searching for sums of 10 and using 10 frame cards. The 10 frame cards are the kind of card you see in the middle of this page, and the Kentucky Center of Mathematics is the resource I recommend for printing the free downloadable version of these cards that you can then print onto cardstock. The Kentucky Center of Mathematics has many really amazing materials that you can download, but it's kind of hard, I find, to find the exact thing you're looking for. So I've included some screen images of the list you're looking for and with an arrow pointing to the exact item. So the number cards 10 frames, that's the one you want to click on to get the template for the 10 frame cards. Once the children, and this probably will be more of a first grade target, but once children are able to do this game very easily without any effort really with the 10 frame cards, then I switch them out so they're working with just the numerals and the 10 frame scaffold is removed. Make 10, Rummy, and Snappo are two other games that are described. The instructions are given at the Kentucky Center of Mathematics, and I've indicated those. And then Make 10 is a little game played with partners where they take turns crossing out or putting colored chips over combinations that make up 10. So through repeated experiences, but varied experiences, children can begin to internalize these sums of 10. By the way, the web link to the Kentucky Center of Mathematics is in the on the references page. All right, also we want children to be able, as they work with 10, to see number decompositions. So sometimes just showing them a particular 10 frame and saying, as a quick image, and say, how do you see this? They can actually, then you put it down, they can try to recreate that image in their mind. So here I've shown 8, and somebody might see a 6. You can kind of see a little dice image hidden there with 2 leftover dots. Some people might say 5 on the top row, 3 on the bottom row, and then you get a 5 and 3 combination. And then I've shown a different version. This would lend itself to a smartboard approach, or an approach where you've got movable magnets on a board that you flash at them, because in this case they can actually say they saw 4 blue and 4 brown, and then you can rearrange them so they can see that 8 is a 4 and a 4 in that familiar pattern. So you really want children to have spent time trying to visualize and experience these numbers and their decompositions as well. All right, I told you that the Kentucky Center of Mathematics would have a web link here, and I will also try to put that web link in our